So today's task was about detecting if the number is power of 4, like power of 2, but a little bit tricky. So I choose this one-liner. It's count 1 bits. We have to have exactly 1 bit set in 32-bit base representations, and then I tried to make this bitmask to all powers of 4, and I have a difficulty to actually reason about it, like how many zeros we should have between each one. So basically, when we doing the power of 4, what we do, we multiplying like 4 by 4, and this is like 2 times 2 times 2 times 2. This each multiplication of by 4 is equal to multiplication by 2 and then by 2. So multiplication by 2 is a bit shift by 1, and that means multiplication by 4 is 2 bit shifts by 1, or bit shift by 2. So basically we have the bit representation. We have 1 for the 1, and then we do 1 bit shift and then second bit shift, and then we do this one again. Oh, I'm so sorry, I apologize, this is not correct. So we're doing a 1 bit shift, and instead of placing this one, we do another bit shift. So this would be 2 bit shifts, like bit shift 1 and bit shift 2. So that gives us the mask, basically this 0101. Let's look at my history. I solved it many times before, and every time I do this some mistake. Let's look. I just interested what kind of mistakes, like corner cases. Okay, this time I didn't make this mistake. Oh, again. So it's a little bit progress for me. I didn't make this mistake. Okay. So some count trailing zeros. Interesting idea. Maybe this should also work, like, or maybe not. So I have to search for the short-form solution. Yeah, it works. So interesting. Count trailing zeros. So that means we can count how many. We can count the position of the one. So we have 1 and some zeros around it. So in the we can count how many zeros. It would tell us exactly where this bit is set, and it should be on a position like odd and even position. So it should be on even position. That's it. So let's look at another interesting solution. Instead of checking bitmask, we just checking if this n-1 is divisible by 3. Why is that? Imagine we have a number 4 power of k, like our good number. We can rewrite it like this, 2 power of 2k, and then we do this like trick, like it's n, and we do n-1 like this, n-1, and on another part of equation we do the same, -1, and this equals to 2k minus 1, 2k plus 1, and this next is a number theory, like what is this number and what is this number. This is like 2 to the power of k. It's always even number, even. It's 2. And this number is odd because we one step ahead. And this number also odd. This becomes like odd, even, and then again odd. Odd. So this is like a sequence of number, like 3, 4, 5, or 11, 12, 13, and so on. So any sequence of number, and this is another intuition of how we can use this. If imagine we have sequence of numbers like 1, 2, 3, 4, 5, 6, 7, and so on. So starting from 0, basically all the positive numbers. And when we inspect these triples of windows of numbers, we look at them if they so this is the same pattern, like even, odd, even, like odd, even, and so on. So this is like triples, and when we do this checking if it is divisible by 3, it always gives us the same row, like 0, 1, 2, 0, 1, 2, 0, 1, and so on. So it's a repeatable pattern. And when we look at this pattern, we see that in every window, in every triple, there is a number that is divisible by 3. So it always present in every sliding window. So basically, when we hit this two numbers, always some of them are divisible by 3. So basically, when we check that n minus 1 is divisible by 3, that means if it's like that, that means we are in this situation where we have power of 4. That's the solution.